Hi everyone, welcome back. So in this video we'll talk about the autoionization of water. In addition, we will learn about how to calculate pH and pOH. So remember that in a previous video we discussed that water is amphoteric. What does that even mean? Right, so water can act as an acid or a base. So let's write down that equation. So we have two water molecules together. One is acting as an acid. Remember, acids are what? Good, proton donors. The other water molecule has to act as a base, which is a proton acceptor. This process is in equilibrium. So if the acid's donating a proton, that means it's losing one of these hydrogens to this water molecule here, and we're left with OH, or OH minus, right, for the hydroxide, which is the conjugate base of water. And what's the conjugate acid of water? When it gains a proton, it turns into H3O, good, plus the hydronium ion. So always be paying attention to your charges so you don't drop any of those. This is the conjugate acid of water when water is acting as a base. Now, we can write an equilibrium constant expression for the autoionization of water, and that's called Kw. So when you see Kw, the W stands for water, and as always with any equilibrium constant expressions, it's always products over reactants. So Kw is equal to the concentration of hydroxide times the concentration of the hydronium ion. And remember, we do not include liquids, so we will not have anything in the denominator here. So this is a good equation to remember, that Kw is equal to the concentration of the hydroxide times the concentration of the hydronium ions. And at 25 degrees Celsius, which is what we will be working with, Kw is equal to 1 times 10 to the negative 14th. In pure water, the concentration of the hydronium ions is equal to the concentration of the hydroxide ions. And therefore, if you wanted to know their concentrations in pure water, you would take the square root of the ionization constant at 25 degrees Celsius, and that would give you 1 times 10 to the negative 7th. And pH is equal to the negative log of the hydronium ions in solution. So that would be pH is equal to the negative log of 1 times 10 to the negative 7th, which would be 7 for pure water. Now, if we add an acid to our pure water, this creates additional protons, or hydronium ions in solution, right? We're adding an acid, it produces more hydronium ions in solution, so therefore it's definitely going to change the pH because acids are proton donors. The concentration of the hydronium ion increases in that solution. And always remember that at 25 degrees Celsius, hydroxide times hydronium ion is equal to 1 times 10 to the negative 14th. Okay, so it's going to be very important that Remember that equation. All right, so for example, let's say I have a beaker with hydronium ion concentration of 1 times 10 to the negative third molar, and I wanted to solve for the hydroxide ion concentration. Then I would use this equation and rearrange it to solve for the hydroxide ion concentration. So that'd be 1 times 10 to the negative 14th divided by the hydronium ion concentration, which is 1 times 10 to the negative third. So in this beaker, my hydroxide ion concentration would be 1 times 10 to the negative 11th molar. So essentially we can use the autoionization of water, the equilibrium constant expression of Kw, to figure out the concentration of the hydronium ions in solution or the concentration of the hydroxide ions in solution if we're given one and not the other. Just to reiterate this, in an acidic solution, the concentration of the hydronium ions should be greater than the concentration of the hydroxide ions in the aqueous acidic solution. And as you can imagine, if you were to add a base, bases are defined as proton acceptors, and therefore the concentration of the hydronium ion decreases because they're being consumed by the base. The base is pulling those protons in, it's accepting those protons, and therefore the concentration in a basic solution of hydroxide is greater than the concentration of the hydronium ions. So let's talk about the pH scale, which allows us to really think about acidity and basicity here. Remember that pH is equal to the negative log of the hydronium ion concentration That's a formula you should remember and feel comfortable using. If we were calculating the pH of the previous example where the hydronium ion concentration was 1 times 10 to the negative third, then we would get a pH of 3. And this would be an acidic solution. The trend with pH is that if pH is less than 7, your solution is acidic. If pH is equal to 7, it is neutral. If pH is greater than 7, it is basic. And here are some examples in this table here of some common substances and their pH values that you may come across. So for example, limes are very acidic, as you would imagine, with a pH of about 1.8 to 2.0. Then you look at, for example, household ammonia solution has a pH greater than 7, 10.5 to 11.5, so it's very basic. And then physiological pH, human blood's between 7.3 to 7.4. And then down below you see the pH scale and how the hydronium ion or proton ion concentration is related to the pH scale. So kind of like pKa that we discussed in a previous video. You know, pKa is the negative log of the Ka. It's easier to think in pKa because you're working with numbers that are, you know, in the tens, for example, like a pK of 3 or a pK of 10 is easier to imagine than something that is in, for example, scientific notation and is really small by orders of magnitude or really large. So same thing for the pH scale here. It's just easier to think on a scale from 0 to 14 than it would be on this huge scale going all the way to 10 to the negative 14th, right? So that's what we want to be considering here. We're always going to be looking at the pH to identify if it's acidic, neutral, or basic. You can use pOH. So there is a pOH scale. pOH is equal to negative log of the hydroxide ion concentration. So make sure you know that formula there. And the trend is if the pOH is less than 7, then you have a basic solution. If it is equal to 7, then it's neutral. And if the pOH is greater than 7, then it is acidic. So you can see the relationship between the pH scale and the pOH scale in this figure. On the left side of this continuum is acidic solutions that you're looking at, and on the right side is the basic solutions that you're looking at. Now, I find it easier to work in the pH scale just by, what I've learned in the classroom as a student, as well as what I did for research, always thought in pH. So I'm going to show you the derivation that if you ever find yourself in pOH, you can always easily convert to pH if you just remember those trends better and you don't want to get confused between the two different scales. It is up to you though. You may like to work in the pOH scale, and that is totally fine. You can go about these problems in different ways. All right, I'm going to come back to the water autoionization equilibrium constant expression, Kw, is equal to the concentration of the hydroxide ions times the concentration of the hydronium ions. We're going to be working at 25 degrees Celsius, so Kw is 1 times 10 to the negative 14th. I'm going to take the log of both sides. The log of 1 times 10 to the negative 14th is negative 14th. I'm going to split these two up, so when you have something that's multiplied, you can add both of them together and take the log. I'm going to multiply this by a negative 1 all the way through. And then 14 is equal to pOH plus pH. I wanted to show you the derivation in case you needed to derive it yourself if you forget this relationship here. But it's always good to remember that the pOH plus the pH is equal to 14. So if you have the pOH, you can easily calculate the pH from this formula here. Or if you have the pH, you can find out what the pOH is. So this is kind of a handy formula to have just in case you want to go back and forth between the two different scales. All right, so when you see little p, just wanted to point this out to you so it can help you remember these three formulas better, the pOH, the pH, and the pKa, for example. So whenever you see p, it's just a mathematical operator to say take the negative log of something. So for example, when you hear pKa, that's equal to negative log of the Ka. Later on, we'll talk about pKb. That's the negative log of Kb. pOH, negative log of the hydroxide ion concentration. pH, negative log of the hydronium ion concentration. So that's all that that little p stands for. It's just a mathematical operator for negative log. All right, let's do some problems together. Now you can go ahead, pause the video. I highly suggest that you do. Try to use these formulas to figure out the different concentrations, the pH, and decide if it's acidic or basic. And then you can come back and check your work with me. So I just like to write down the formulas to make sure that I can utilize them when necessary. So for example, pOH is equal to the negative log of the hydroxide. Now, if you ever want to figure out, for example, the hydroxide ion concentration from pOH, you've got to take the antilog. And so therefore, the hydroxide ion concentration is equal to 10 to the negative pOH, so the antilog of that. So that's a good formula to remember. It's the same for pH. So pH is equal to the negative log of the hydronium ion concentration. And therefore the hydronium ion concentration is equal to 10 to the antilog to the negative pH there. By the way, that H there stands for proton, but we're writing the hydronium ions because we understand that protons don't exist just by themselves in aqueous solution. They exist as hydronium ions. All right, we also know that, a good formula just to have in our pocket is pH plus pOH is equal to 14. This particular problem doesn't ask about pOH, but I just want to make sure you feel comfortable with it. And then also the water ionization equilibrium constant expression is so good to have, so you can go back and forth between hydroxide and hydronium ions in an aqueous solution. This is equal to 1 times 10 to the negative 14th, 25 degrees Celsius. All right, got the formulas written down. Just look at the first row here. We're given the hydronium ion concentration. We want to figure out the hydroxide ion. So to do that, I would use this formula down here. I would take 1 times 10 to the negative 14th and divide by 3.5 times 10 to the negative 3rd. And when you do so, you should get 2.9 times 10 to the negative 12th molar. Now remember, the pH of the solution is equal to negative log of the hydronium ion concentration. So negative log of 3.5 times 10 to the negative 3rd. And when you calculate that, you should get 2.46. Now the rules for significant figures, when you take the negative log of something, you always add a significant figure here. So you notice we have 2 sig figs here, but when I took the negative log of 3.5 times 10 to the negative 3rd, I had to add another significant figure. It's just the rules for logs and natural logs. Now if you do the anti-log, then you have to decrease by a significant figure. So that's why a lot of times you see pH in 3 significant figures, and then that's because the hydronium ion concentration was in 2 significant figures. Now because the solution has a pH of 2.46, this is considered acidic. It's less than 7. All right. Now, in the next row here, we're given the hydroxide ion concentration. So you use the Kw expression to figure out the hydronium ion. So you would take 1 times 10 to the negative 14th, divided by 3.8 times 10 to the negative 7th, and you should get 2.6 times 10 to the negative 8th molar. The pH is negative log of the hydronium ion concentration, so negative log of 2.6 times 10 to the negative 8th. It's 7.58, which is greater than 7. This would be considered a basic solution. In the next row, we're given the hydronium ion concentration. We use the Kw expression to figure out hydroxide. you should get 5.6 times 10 to the negative 6. The pH is the negative log of the hydronium ion concentration. That should be 8.74, which is greater than 7. So is it acidic or basic? Definitely basic. Good. And then in the last row here, we are given the pH. And so from there, we can figure out the hydronium ion concentration. So we do the anti-log 10 to the negative pH here. And the hydronium ion concentration, when you plug that in, 10 to the negative 7.15, you're going to decrease it by one significant figure. You should get 7.1 times 10 to the negative 8 molar. Then from there, you can figure out your hydroxide ion concentration from the Kw expression. You can take 1 times 10 to the negative 14th and divide it by 7.1 times 10 to the negative 8th. You're going to get 1.4 times 10 to the negative 7th molar. The pH is a little over than 7, so if you had to decide acidic or basic, you would say basic, but it's pretty close to neutral, right? I would say. All right. Well, thank you all for watching, and I'll see you next time.